The topic of today's video will be zeros and poles, and as we have been discussing this topic in our last video, so I will take some examples of zeros and poles, right? Example number 1, find the zeros and their nature of function fz equal to z square 1 minus cos z, right? So this is a function, you have to find its zeros and their nature, right? Okay, and zeros and the order, sorry, right? Solution: in order to find zero of a function, you can just equate that function equal to 0, right? In order to find its zeros, from here I will obtain z equal to 0, right? Obviously that will be obtained twice, right? And from here I will get cos z equal to 1, and cos z equal to 1 gives z equal to 0, 2 pi, 4 pi, right? Means even multiple of pi, 2n pi, right? Where n is an integer. Okay, so you see that z equal to 0 is obtained from this z square, and from this 1 minus cos z you obtain z equal to 2n pi, right? And n is an integer, right? Okay, and if you focus on this 0, you'll see that if I plug n equal to 0, because 0 will belong to this integer set, if I plug n equal to 0 here, then I will get z equal to 0, right? It indicates that z equal to 0 is obtained from z square as well as from this function, so that should be given a special treatment. Z equal to 0 is a 0 of this function, and we'll consider that separately, right? Because that is obtained from two different functions, right? Okay, so all of them are zeros, right? Are zeros of fz, right? Now I will investigate the order, their order also. First I will consider this z equal to 0 for z equal to 0, right? In order to find the order of this 0, what I will do, there are two ways actually. One way is to get the Laurent's expansion of this, or Taylor's expansion, whatever, in powers of z, right? And the other way is to treat this function as gz and fz and its derivative and so on, right? So I will use the expansion here, because since we are having this cos z here, and you know the expansion of cos z, right? So expansion method should be used here, right? So just writing the expansion of cos z, that will give me 1 minus z square over 2 factorial plus z to the power 4 by 4 factorial and so on. And you can see that this 1 and 1 will be cancelled, right? And after cancellation, this will become plus z square by 2 factorial minus z to the power 4 by 4 factorial and so on, right? And then you can take z square common, and we'll be having z to the power 4 here, and inside bracket I will be having 1 by 2 factorial minus z square upon 4 factorial and so on, right? So we have expressed our function in this form, z to the power 4, and this is my gz, right? I'm treating this series as a gz, and you can see that you have expressed your function, given function fz, as a product of two functions. The first is z to the power 4, or you can say z minus 0 to the power 4, and this function is non-zero. If you plug z equal to 0 here, right, then it will become 1 by 2. It means that this gz is a non-zero, right, and it is analytic at z equal to 0, obviously. Therefore, or I should write it here, where g0 is not equal to 0, you can see, right, and gz is analytic, right, at z equal to 0. So you can say that z equal to 0, right, is a 0 of order 4. Okay, or you can use that alternate definition also, the formal definition to find the order of a 0, you just differentiate it 1 times, 2 times, 3 and 4 or 5 times, right? And then you will see that if you plug 0 in all of those derivatives, then up to third derivative, f0, f dash is 0, f double dash 0 and f triple dash 0, they all will vanish, right? But its fourth derivative will not vanish at z equal to 0, right? But finding the derivative will be complicated as compared to this one, because this is a product of two functions. I have to apply product rule repeatedly, right? That's why I have used this expansion method, right? Okay. Now since we have treated z equal to 0 separately, now I will treat the other zeros. The other zeros are z equal to 2n pi iota, where n is not equal to 0, right? Okay. So I will name it A step, and this is my B step for z equal to 2n pi, and n is any integer other than 0, because this case has been discussed here, right? Okay, z equal to 2n pi, fine. So this time I will use that derivative rule. I will differentiate that fz and check their values at this point, right? Okay. Now fz is given, that is z square 1 minus cos z, right? F dash z can be obtained easily. You can differentiate this using product rule, that will give you z square sin z, and I think twice of z 1 minus cos z. Then f at 2n pi, if you plug 2n pi here, right, in the function, you will get 2n pi square and 1 minus cos 2n pi, and cos 2n pi is actually equal to 1, right? So that will give you 0, right? Okay, and this will also be 0. I think I have to find the second derivative also. F dash 2n pi will be equal to, if you plug 2n pi here, that will become 0. Sin 2n pi is 0, and since this is cos 2n pi, again it will become 1, and we will get 0, right? It means that I have to find the double derivative also. I need a non-vanishing derivative, right? And so far we are having a vanishing derivative, so I will find f double dash also, right? F double dash z, and on differentiating it, I will get z square cos z, and this is a good term, right? It will not go to 0 if I plug 2n pi here, okay, plus 2z sin z, and it is 2, then minus 2z cos z, then it will become plus 2z sin z, and I think minus 2 cos z, right? And if you plug 2n pi here, then this term will become 4n square pi square, and cos 2n pi becomes 1, right? This will be 0, this will be 0, and we'll have 2, and this term will be cos 2n pi will be 1 minus 2, right? So ultimately these terms will be cancelled, and we'll be left with 4n square pi square, that is not equal to 0, right? And remember that n is not equal to 0, right? We are considering the case for those zeros for which n is a non-zero integer, right? So it cannot be equal to 0. That's why I have written inequality, not equal to here, right? Okay. So we can say that we have the second order derivative, this second order derivative, which is non-vanishing. So the order of this 0 will be 2, right? Therefore z equal to 2n pi, where n is an integer other than 0, is a 0 of order 2, right? So you have to take cases separately, especially for that number which is appearing from both the functions, like this 0, it is appearing here also and here also, right? So treat that separately. Okay, taking another example, example number 2. find the poles and their order, right, for the following functions. Solution. First part is 1 minus cos hyperbolic z over z to the power 4, right? You have to find its pole and its order, right? Okay. So in order to find its pole, you can see that the denominator is becoming 0 at z equal to 0, right? And obviously, if you put z equal to 0 in the numerator, you will get 0 in the numerator also, right? It means that you are getting 0 by 0 form at z equal to 0, right? But be careful at this point. Z equal to 0 may be a removable singularity. Sometimes we get 0 by 0 form, but on applying LH rule, L'Hospital's rule, we get a number, right? In that case, it is a removable singularity, right? But what happens here, if I put 0 in the numerator and denominator, I am getting 0 by 0, that is fine. And if I apply LH rule, then the numerator will become sine hyperbolic z minus sine hyperbolic z, and denominator will become 3z or 4z cube. Again, I will get 0 by 0 form. And if I again apply that LH rule, I will get cos hyperbolic minus cos hyperbolic z upon 6z, I think, something like that. In that case, I will get infinity, because the numerator will be equal to 1 and the denominator will be equal to 0. In that case, it is clear that z equal to 0 is singularity of this function, right? Okay, so I can write that z equal to 0 is a singularity of this function, right? Okay. Clearly, z equal to 0 is a singularity, and you should know why I am writing it, why we are calling it a singularity, right? Okay. Now, in order to find the nature of the singularity, or we can say, is it a pole, or is it essential singularity, or it is a removable singularity, right? So we have to rely on expansion. If we expand this cos hyperbolic z, right, then we'll get the answer, right? And I will apply expansion, expanding fz. I'm writing it at fz equal to 1 over z to the power 4, 1 minus, and its expansion will be containing all even powers of z, right? We have plus there, okay? Even powers of z, that will give me 1 plus z square by 2 factorial plus z to the power 4 by 4 factorial plus so on, right? So you have to remember this expansion for cos hyperbolic z. Cos hyperbolic z is nothing, but it is actually equal to e to the power z plus e to the power minus z divided by 2, right? So use the expansions for e to the power z and e to the power minus z separately, and if you add them, you will get this expansion, right? All even powers of z. And similarly, for sine hyperbolic z, we have all odd powers of z, right? Okay, and you can see that this 1 and 1 will be cancelled, and we can take this z to the power 4 inside, right? And on cancellation, I will be having minus, I think, 1 over z square 2 factorial, and this term will be minus 1 over 4 factorial, okay, and minus so on, right? Or I can write one more term here. If it is z to the power 6 upon 6 factorial, then I will be having minus z square over 6 factorial and so on, right? And after this term, we will have positive powers of z. There is a constant term, and there is the only negative power of z, right? It indicates that in the Laurent's expansion about the point z equal to 0. Why I am saying that this expansion is at about z equal to 0? Because all the powers are of z, right? Okay. So in its expansion, you can see that there is only one term in the principal part, right? The part containing negative powers of z, there is only one term. So we can say that z equal to 0 is a pole, right? And what is the order of that pole? You focus on this term. If you see that the maximum negative power of z is 2, So the order of the pole is 2, right? Okay. Since the principal part contains finite terms, therefore z equal to 0 is a pole of order 2, right? And you should know the reason why I'm writing pole of order 2 only. Okay, taking another example, B part, right? If I take 10z, right? Okay, so solution, we can write it as fz equal to sine z over cos z, right? Sine z over cos z, right? And in order to find its singularity, we should check where the denominator is 0, right? And you can see that this denominator is 0 if z is odd multiple of pi by 2, right? And this n belong to z, yeah, z. Okay, so these are poles, or you can say singularities, right? And obviously if you plug any of these values here, z equal to 2n plus 1 pi by 2, the denominator is going to 0, but the numerator is not going to 0, that is 1, I think, right? So it is a singularity, obviously, that is clear, and all of them are poles. And why I'm writing that they are poles, right? Without expanding it, I know that they are poles. Why? I'm explaining it, why I have written this, they are poles, right, at this point. If you focus on the denominator, you can see that we can write this as sine z over gz, right? I'm using one of the result obtained in our previous video. I'm writing this function as sine z over gz, right? And we know that the order of the 0 of this gz, right, is actually the order of the pole of fz, right? And you see this function, this is actually your gz is cos z, right? Okay, so if you take this gz equal to this here, gz equal to cos z, right? And if you differentiate it, g dash z, you will get minus sine z, right? And you can check that g at 2n plus 1 pi by 2, the value of the function is 0, obviously, right? But its first derivative is equal to minus 1. Sine of odd multiple of pi by 2 is equal to 1. So this is not equal to 0. So you can say that, focus on this part, the denominator function, right, has a 0 at 2n plus 1 pi by 2 of order 1, right? And that indicates that fz will have a pole of order 1 at that point, right? As we derived the result in our last video, that zeros and poles of a such function, which is written in this form, pz over qz, are related, right? So you just find the nature of 0 of this gz, and ultimately you get a direct result for the poles of fz, right? So focus on this calculation, and we can write that, that is gz has a 0 of order 1, or you can say simple 0, at z equal to 2n plus 1 pi by 2, right? Which implies that fz has a simple pole means poles of order 1, at z equal to 2n plus 1 pi by 2, and n is an integer, right? So you can use that result also, right? And finding zeros and poles, especially poles, need some skills, right? Sometimes you have to rely on the expansion, like I use in this for A part, and sometimes you have to rely on that result, the relationship between the zeros and poles. Okay, right? Taking another example, C, if you take function fz equal to e to the power z plus 1 over e to the power z minus 1, right? And again you see that your function is of the form pz over qz in that form, right? So in order to find its poles, I will focus on the denominator part and I will write it as e to the power z plus 1 over gz, right? So I'm interested in finding the zeros of gz and their nature also, right? So ultimately I will get the result for fz. Okay, put gz equal to 0, right? And if you put gz equal to 0, you will get e to the power z equal to 1, and since this is 1, this is not e to the power 0 only, e to the power 0 is 1, right? But since we are dealing with a complex number, so we should write e to the power 2n pi eta, right? So this is a more general value of 1, right? And n is obviously any integer, so we will get z equal to 2n pi eta, n is any integer. So all of these are I have to declare here that they all are poles, and why they are poles you should know it, because yeah, n equal to, if I put 0 1, okay, 0, yeah, all of them are poles, right? Okay, because each of these points, at each of these points the numerator is non-zero, right? If you plug this 2n pi eta here, you will get, I think, 2 in the numerator. It indicates that the numerator is not vanishing, but the denominator is vanishing at that point, so they will be poles, right? And again, there will be singularities, okay, sorry. And why I am writing that they are poles, because I know that if I do the derivative of this gz, then after the first derivative, I mean the first derivative will be non-vanishing at that point, right? Okay. Now gz equal to e to the power z minus 1, and if you differentiate it, you will get e to the power z, and immediately you check that g, since g at this 2n pi eta is equal to 0, but its first derivative is equal to e to the power 2n pi eta, that will be, I think, 1, cos 2n pi plus eta sin 2n pi, that will be 1. It is not equal to 0. So you can conclude that the denominator function, this function, right, has a 0 of order 1 at this point, right? And if the denominator function has a 0 at some point, then the whole function, the complete function, has a pole of that order at that point, right? Therefore gz has a simple 0 at z equal to 2n pi eta, where n is an integer, right? And which implies that your function fz has a simple pole at z equal to 2n pi eta and belong to z, right? Okay, let me take another example. Example number 3. And yes, a point, right? Function is fz equal to e to the power z plus 1 over z, right? Investigate its behavior at z equal to 0, right? So you have this function and you have to investigate its behavior at this point, right? Solution. So what I will do, I will expand this, my function, in powers of z only, because we have the singularity at z equal to 0. I don't know the singularity, but why I am saying that this is a singular point. At this point the function is not analytic, right? If you plug this z equal to 0 here, then it will be e to the power 1 by 0 and e to the power infinity and so on, right? So you are getting infinite, right? So we cannot say that this is an analytic point of this function. At this point the function is not analytic, right? So something is happening at this point, right? So this is a singularity of this function, because the function is not analytic at this point. It means that this is a singular point of this function, right? And to find the nature of singular point, you can rely again on expansion. You can write it as e to the power z e to the power 1 by z, right? And then you expand it. You write the expansion of both of them, 1 plus z square by 2 factorial and so on. And for this, 1 plus 1 by z plus 1 by z square over 2 factorial and so on, right? And then you multiply these two, right? Obviously on multiplying you will get 1, okay, and 1, and okay, so many ones will be there, right? So constant term will be there, and yes, I think negative powers will also be there. However, I cannot write the whole expansion, but do not multiply them. If you see it closely, you will find that if you multiply this one by this whole series, right, then you will multiply this z with this whole series. I will write just one of them, 1 plus 1 by z over 1 upon 2 factorial z square and so on, right? So you can see that there are infinite negative powers of z in the first part. Similarly, if you multiply z with this whole, right, 1 plus 1 by z plus 1 upon 2 factorial z square and so on, right, and up to infinity, right? So this part will give infinite negative powers of z. Similar for this part also, right? Except the first two terms, the rest of the terms will contain negative powers of z, right? And similarly in third bracket, except the first three terms, all the rest of the terms will be containing negative powers of z. So ultimately you will be having infinite negative powers of z, right? So you can say that z equal to 0 is an essential singularity, right? Whenever the Laurent's expansion containing infinite negative powers of z minus z naught, right? Here we have z naught equal to 0. We can say that that is an essential singularity of that function, right? Okay. Taking another example. Example number 4. If fz equal to z plus 1 cos 1 over z plus 2, right? Investigate the behavior of fz at z equal to minus 2, right? So if you plug this z equal to minus 2 here, obviously we'll get cos 1 over 0, right? And that is sufficient to say that z equal to minus 2 is not an analytic point of that, right, function. Okay, so you can say that this will be a singular point, and if it is a singular point, we have to investigate its behavior, and again we have to rely on that expansion. But this time we are interested to examine the behavior of this function at this point z equal to minus 2, right? So you will be required to find an expansion in powers of z plus 2. That is the important point here, because the center of the series should be minus 2. So take this minus 2 here, you will get z plus 2, right? So the expansion will be in powers of z plus 2. The important point is that, okay. And since I need, I will write note here, right? You need expansion. We need expansion in powers of z plus 2, right? And to achieve this goal, we can write fz as z plus 2 minus 3, right? This z minus 1 can be written in this way because I have to create z plus 2 everywhere, right? And cos 1 upon z plus 2, this is fine. And then I will multiply them, z plus 2 multiplied by cos 1 over z plus 2, this is the first function, and then minus 3 times cos 1 over z plus 2. Now I have two functions. The first is containing z plus 2 and the other one is also containing z plus 2. Now you can expand these two, z plus 2, okay, and using expansion of cos theta, that is 1 minus 1 plus 1 over z plus 2 whole square by 2 factorial, then plus 1 over z plus 2 whole to the power 4 over 4 factorial minus dash dash dash, and the second expansion will be minus 3 times 1 minus 1 over z plus 2 square over 2 factorial and so on. Right. Now you can multiply your z plus 2 inside. You will ultimately get z plus 2, right? This is the only positive power, I think. Yeah, z plus 2. You multiply z plus 2 with this one, you will get minus 1 over 2 factorial z plus 2, and you multiply this with this one, you will get cube term, and from here you will get minus 3. I should write that minus 3 here, I think. Minus 3. This is plus. Okay. So minus 3, and from here I will get a square term, that will be minus plus 3 by 2 factorial z plus 2 whole square and so on, and the rest of the terms will be containing negative powers of z plus 2. You can see from here it starts from negative power, start from this point and up to this point. This is constant term, this is positive power z plus 2, so this will belong to the analytic part, and all of these terms will belong to the principal part. And you can see that the principal part is containing infinite powers of negative powers of z plus 2. So we can say that z equal to minus 2 is an essential singularity, right? So I'm not writing the reason, right? I'm writing the result directly. Z equal to minus 2 is an essential singularity. And why I have written this, you should know the reason, right? From Laurent series, principal part of Laurent series, right? Taking another example. Example number 4. Investigate the nature of singularities of fz equal to z minus 1 e to the power 2 pi eta over z minus 1, right? So this is a function, and you can see that again this is of the form pz over qz, right? You have to identify its singularities, right? And in order to find the singularity, you equate this denominator equal to 0, right? But keep in mind the fact that if you get some point, suppose you get z equal to alpha, right? On equating this denominator to 0, and at that point the denominator should not be vanishing. Keep in mind the fact that, okay? So solution, if you put or equate this e to the power 2 pi eta over z minus 1 equal to 0, you will get something like this: e to the power 2 pi eta over z equal to 1, and that 1 can be written as e to the power 2n pi eta, where n should be an integer, right? And then comparing their exponents, I will get, I think, 2n pi eta by z equal to this much, then 2 pi eta will be cancelled out, and I will be getting z equal to 1 over n, right? And obviously n is an integer, right? Okay. And yes. And if you see that, if you have n equal to 1 here in this set, right, and you will get z equal to 1 in that case, right? But there's a danger at that point, because z equal to 1 is, if plugged in the numerator part, that is also going to 0, right? It means that z equal to 1 has to be given special treatment, right? Okay. So I will treat z equal to 1 separately. And why separately? Because at z equal to 1, the numerator is also going to 0, right? Okay. For n equal to 1, right, are poles, right, are singularities. I should write here singularities, right, not poles, because this is including the danger point z equal to 1, right? Singularities. Okay. So for n equal to 1, we will have z equal to 1. A singularity. Obviously, this is singularity. But to judge the nature of the singularity, what I will do, I will plug this z equal to 1 here, right? Now f at 1, or you can say that the limiting value of limit z tends to 1. I am interested in finding the value of this function at z equal to 1, right? However, z equal to 1 is the singularity, right? Okay. So the value of the function, the limiting value of the function at z equal to 1, z tending to 1 can be obtained as limit z tends to 1, z minus 1 e to the power 2 pi iota over z minus 1, right? And if I put z equal to 1 here, I will get 0 by 0 form, you can see, right? 0 by 0 form, because e to the power 2 pi iota is 1 actually, right? This is pi. Okay, so I have to apply LH rule. Limit z tends to 1, the differentiation of the numerator will be 1, and the differentiation will be e to the power 2 pi iota over z, and that should be multiplied by, I think, minus 2 pi iota over z square, right? So this is the result after applying LH rule. And if I plug z1 here, then now it is fine. The numerator is 1, and it will become e to the power 2 pi iota, that is 1, and we will get minus 1 over 2 pi iota as the answer, right? So you can say that if z approaches 1, then the function is having some value, not infinite, right? It indicates that it is a removable singularity. Remember the case for the function sin z over z at z equal to 0. If you plug z equal to 0 in sin z over z, you will get 0 by 0, but on applying LH rule one time, you will get 1 as the answer. That's why we call z equal to 0 is a removable singularity of sin z over z. That is the same case happening here, right? We are getting a finite value when z approaches 1. So we can say that z equal to 1 is a removable singularity, right? Therefore, z equal to 1 is a removable singularity, right? And one more approach to find the nature of singularity at z equal to 1, you can expand this function in powers of z minus 1. The thing is that you have to expand this function in powers of z minus 1 if you want to investigate the nature of the function at z equal to 1. But since the expansion will be quite difficult, in order to obtain an expansion in powers of z minus 1, I have to do manipulation here, z minus 1 plus 1 here, this part, and then apply expansion. That will be quite complicated, right? So as I have already said that we have to use any result, as we studied in our last video, according to our need, right? So z equal to 1 case is treated here, and what about the other singularities like z equal to 1 by 2, z equal to 1 by 3, and so on, right? Okay, I will treat them separately. So I will write it as A, and for the other singularities, if n is equal to, and I should write here n is z oblique 0. 0 should be deleted here, right? Because that is producing z equal to infinity, right? N is plus minus 2, plus minus 3, and so on, right? Any of these values. Okay. So for these values, right, z will be equal to 1 by n. Okay. And I will check the nature of my singularity by investigating the denominator of that function. If you see the denominator part, at any of these points, if n equal to plus minus 2, then z will be equal to 1 by n, obviously, right? At any of these points, suppose you pick any of these points 2, then z equal to 1 by 2, right? Or you can choose 3, then z equal to 1 by 3. At any of these points, z equal to 1 by 2, 1 by 3, the numerator is analytic and not equal to 0, right? And now I can use that result when the numerator is analytic at some point, right, at that point and non-zero, then the 0 of the denominator decides the pole of the whole function, right? Clearly, the numerator that is z minus 1, is not equal to 0 at these points, any of these points, right? Okay, then I am taking the denominator gz equal to e to the power 2 pi eta over z minus 1, right? And it is the denominator of that function, and I will differentiate it, g dash z, that will produce e to the power 2 pi eta over z minus 2 pi eta over z square. You can see that g at 1 by n, right, is 0, but g dash at 1 by n is not equal to 0. You can check it from here, right? So the denominator function has a simple 0 at z equal to 1 by n, right, and where n is not equal to 1, obviously, right, and this n is belonging to z oblique 0, right. 0 case has been treated separately, 0 has been deleted, right, from our set, and n equal to 1 case has been treated separately. So this is, result is for the remaining poles, right, simple zeros, or you can say that your function fz has a simple pole at z equal to 1, right, where n is not equal to 1, that is separately discussed, and all of n are non-zero integers. So this is the final answer, right? Okay, taking another example. Example number 5. Expand the function fz equal to 1 over z minus 1 in the region mod z greater than 1, right? Comment about the nature of singularity of fz at z equal to 1, right? So obviously you need Laurent's expansion sometimes to comment about the nature of singularity, right? So the question is asking you to get a Laurent's expansion for this domain, and then you have to comment about the singularity, right? Okay, so solution. First I am expanding this function inside this region for mod z less than 1. I can write my function using partial fraction. You know that you have to write your function as a sum of partial fractions. Then it will become z minus 1 minus 1 over z. If you take LCM, you will get this, right? Okay. And again, now you have to take decision. First thing is that you see the center of this disk, right? This center is 0, right? Okay. So the resulting series, the final series, should be containing the powers of z only. First thing is that. So this term will be undisturbed because this is already containing z minus 0. So I will not touch this term. I will do manipulation here, and to manipulate this, whether I should take z common or 1 common, right? So I should take 1 common, right? Because mod of z is, I should take z. Yeah, I should take z common. Mod z is greater than 1. Okay, I will take z common, then it will become 1 over z is less than 1. Okay, z common, it will become 1 minus 1 over z, right? Okay. And from here I will get minus 1 over z, right? And the reason for this thing, 1 minus 1 over z, why I have taken z common? Because I know that the modulus of this number should be less than 1. So I am writing the reason here as mod z greater than 1 gives 1 over z less than 1, right? So that's why I have created 1 over z here, right? Okay, so this is an important step, that what should be taken common, z or 1, right? You should create a function here such that 1 minus alpha, and this alpha, mod of this alpha should be less than 1, and that is obvious from this domain, right? Okay, so now I will expand it. 1 by z, I will take this in the numerator, 1 minus 1 by z whole to the power minus 1 over z. I will get 1 by z, 1 plus 1 by z plus 1 by z square plus 1 by z cube and so on, and minus 1 by z. I think this 1 by z will be cancelled, and ultimately I will be having 1 by z square, 1 by z to the power 3 and 1 by z to the power 4 and so on, right? So you can see that all of the powers of z are negative powers of z, and that indicates, obviously, the first thought is that z equal to 0 is an essential singularity, but that is absolutely wrong, right? However, the Laurent expansion is containing infinite negative powers of z, right, in its principal part. So the first tendency is to say that it has an essential singularity at z equal to 0, but that is not true actually, right? Why it is not true? Because you cannot comment about the nature of singularity at z equal to 0 at this point, because see your domain, right? The reason is that your domain is the point, your domain is this, mod z greater than 1 is the outside of unit disk, right? Your domain is this thing, this is your domain outside of this disk. This point is 1 and this point is 0. You can see that z equal to 0 and z equal to 1 are the singularities of this function, obviously. So this is 0, this is 1, and you have expanded this function for this domain outside of this disk, and you can see that this disk has a hole here, but inside that hole you have two singularities, 0 and 1, and that's why on watching this result you cannot comment about the nature of singularity at z equal to 1, right? So z equal to 0, sorry, z equal to 0, sorry, z equal to 0. Okay, you cannot comment about this nature of singularity at z equal to 0, because this hole is enclosing two singularities, 0 and 1, right? So the correct comment or the correct result can be obtained if you expand this function not in this domain but in this domain. I should write that domain here. This domain, the inside circle, means the circle centered at 0 and radius equal to 1, that should be 0 mod z less than 1. This should be the domain, right, inside which you should be expanding your function to comment about the nature of singularity at z equal to 0 correctly, right? So do not comment at this point, because your domain was enclosing a singularity other than z equal to 0, right? In order to make a correct comment about the nature of singularity on seeing the Laurent's expansion, you have to create a domain such that it encloses only that singularity, right? So we cannot comment about anything after seeing this expansion, right? In order to comment correctly, you have to expand your function in this domain, right? And in that case, after getting Laurent's expansion, there will be only one negative term with the negative power term, that will be 1 by z, I think, right? And all the terms will contain positive powers of z, and then z equal to 0 will be a pole of order 1, right? Okay, or the another way is, without this expansion, you can just write it as fz equal to 1 over gz, and you should see the nature of 0 at z equal to 0 for the denominator function, and that should be obviously a simple 0, right? And again fz will have a simple pole at that point, right? So choosing Laurent's expansion but choosing a domain is also important, right? You cannot just rely on expanding your function, right? You should choose the correct domain in order to comment about any point, any singularity correctly, right? So this is it for this video. Thanks.